Hi there, Chemistry 11 again. So, yeah, I didn't cover much for a little bit, had some other stuff going on, and now I'm going to get going also today with a lab that will be due next week. The title of the lab is the formula of a hydrate. Just a reminder, hydrate is a special kind of ionic compound. A lot of ionic compounds like salt, sodium chloride, is just sodium and chlorine, the chloride ion. Now, a hydrate is a regular ionic compound, but locked into the crystal structure are molecules of water. And they show that using a little dot after the formula. Let me show you what that looks like. So, here's one. Not the best one to start with, but this is the one that we're looking at today. In the middle of the screen, KAl, SO4 with 2, and then we see something H2O. Now, here, I'm going to give you an example of another one that I had in the lab earlier today. And that is this. CuCl2.2H2O. Let's consider that one. You will, I think, remember that the chloride ion has a -1 charge. There's 2 of these chloride ions here. This means that this copper has to have a +2 charge. We call this copper 2 chloride. But there's also water locked into the crystal structure. So we call it also a dihydrate. The di means 2, the hydrate means water. The crystalline structure of copper 2 chloride dihydrate has 2 water molecules locked into the crystal structure for each formula unit of the copper 2 chloride. That makes it a hydrate. What you can do that's pretty cool is you can actually start a decomposition reaction. A decomposition reaction, Science 10, you are taking a chemical compound, single chemical compound, and you are maybe putting it, subjecting it to some kind of stress, maybe heating it up, and the chemical compound breaks down into more than one compound or maybe more than one element, depending on what your reaction is. Now, what's really cool with this lab is that if you have the formula for the ionic compound, just the ionic compound without the water, and you can measure masses with the hydrate, remove the water, and then measure the end mass, you can actually calculate what the ratio is of water to the salt itself, to the ionic compound. In other words, you can figure out what the formula is for that hydrate with reference to how many water molecules are locked up with each formula unit. I'm going to give you air quotes here saying each molecule of the ionic compound. We shouldn't really use that language for ionic compounds because they're in formula units in crystals. Here's what we're going to do. Here's how we're going to start. I'm going to demonstrate the lab with one compound, and then I'm going to give you the results for a different compound. So here's where we're at. Now, I actually have some results in here already. What happened is I was doing this lab earlier today and had a bit of a blooper, I guess is the expression. Something came up and I stopped the video because I wanted to make it better. So as a result of that, I actually already have some data in there. Aluminum potassium sulfate is also called alum. It's used for pickling meats. It's a fairly safe compound to work with. It's also a hydrate. Now, the stuff that you get out of the chemical cabinet is aluminum potassium sulfate dodecahydrate. That means it's got lots of water in it. Every formula unit of that compound has got 12, as in dodeca, water molecules around the ions. Now, the thing is this. What you can do is you can take that material. This is a common science fair project. You can boil it, and then you can let it sit. And what happens is crystals will form at the bottom of your vial after you've done that. If you've made what's called a supersaturated solution, crystals will form at the bottom, which is very pretty. You get these big crystals. The thing about these crystals is they're not dodecahydrate. A different number of water molecules associates with the crystals when they're formed in a neutral solution. And the question is, what is that number? How many water molecules associate with each formula unit of the aluminum potassium sulfate? Doing a slab, we're able to figure it out. First of all, I'll show you what the crystals look like. You go to the grocery store, you can buy this stuff. Let's get that up close to the camera. There. You can see very pretty crystals. You can get them way bigger than this. I did this earlier with another crystal of it, and I'm going to go through the masses in a sec. In fact, well, I might as well do them now. I'll tell you what it all looks like when it happens. The first thing I need to do is to measure the mass of the crucible. This is a crucible. You can heat these up really hot over a Bunsen burner. The crucible had a mass of 20.63 grams. Then I put a crystal of the alum in there, into the crucible, and this is the mass I got after that. This allows us to calculate the mass of the sample. That's pretty straightforward. That's 22.03 minus 20.63. Let's get a calculator to figure that out. .03 minus 20.63. And I'm getting 1.40 grams. What is that? That figure, 1.40 grams, is the mass of the hydrate salt. That's the mass of the crystal I put in there. What I did then is I took that hydrate salt and I put it in the crucible and I heated it up. In fact, it's still in here. What I'm going to do is I'm actually going to start the Bunsen burner up again because I want to make sure this is as dry as possible. The better you are at getting the water out of there, the more likely you are to get a good result. I don't know for certain if this happens, but I kind of suspect that if you leave the dried out salts out in the open air, I think they might absorb water, and that's my concern. There we are in the middle. What I saw, when I did this earlier, is we started out with this pretty little crystal. I put it into the crucible, heated it up to several hundred degrees. The crystals break up. Water locked up in the crystals starts to boil. As you started with this clear crystal, you end up with this kind of a bubbling mass, and then you get what you saw in there, which is kind of it looks like a little meringue or something, kind of basically just a little white thing. And what we're going to be able to measure just now will be the mass of the dried sample in crucible. Now this is going to take a couple minutes, so I'm going to run you through the kind of calculations we're going to do, and then we'll be able to do those faster. So I'm going to get the mass of the dried sample in crucible in a moment. From that, I'll be able to calculate the mass of the dried sample. An ionic compound that doesn't have water in it is called an anhydrous. I think it would probably be called an anhydrate. You describe it as anhydrous. It's got no water in it. The water is boiled away. We'll be able to calculate that because I'll have the mass of the dried sample plus the crucible. I will do what I did before. I'll subtract the mass of the crucible to get this, the mass of the anhydrous compound. But this is the smart bit. Having the mass of the anhydrous compound, I can then take the mass of the hydrate and subtract the mass of the anhydrous compound. That will tell us how much water is in there, and that's where things get really interesting. It'll tell us the mass of the water. All this is in grams. Then we need to go to chemical amounts. And this is where the ratios come in that you're seeing coming up in the worksheet I just assigned. Let's have a look at this. I'm going to put the flame on it a bit more, see if I hear any crackling. Okay. This is super hot. Just about ready. The other thing is I don't want to burn my fingers. Okay. Just a sec. Okay. So, can we say contamination? Here I am holding this thing for you. You can think of all kinds of sources of error, I'll bet, based on the way I just picked that thing up. Here is a crystal of copper sulfate. This will be the subject of your lab. All I'm going to give you will be the raw data. Here I'm going to show you the answer. For this one, I'll be relying on you to find the answer yourself based on my walking you through it. The copper sulfate pentahydrate is a very pleasing blue color, as you can see. Very big crystal of this stuff. But how many water molecules are locked up in each of those 4 millunits of copper 2 sulfate? Okay, I'm not hearing any crackling at all. I'm going to switch that off. So the next thing we need to know, we need to think about, is this. We need to think about what are the chemical amounts that are present based on our mass values. To do that, we need the molar mass. We need the molar mass of the anhydrous potassium aluminum sulfate, the version that has no water in it, the version that I made here that's that white meringue looking thing. How do we get that? We add up all the molar masses of the elements, where each one will be multiplied by the subscript for that element. Have a look at this. Here's where I will recommend you bring out your periodic tables. Either the photocopy from a Science 10 textbook, or that you should bring out, open up the dynamic periodic table online to get these kinds of results that I'm about to show you. Each of the 4 millunits has one potassium ion, one aluminum ion, and then, now we've got to count out the other atoms, don't we? Well, sulfur, it's got 2, because it has 2 sulfates in each of the 4 millunits. This is what we need to balance the charges. How about oxygen? Each sulfate has 4 oxygens, and there's 2 of them. 4 times 2 is 8. We have 8 oxygens. Each of these values will be multiplied by the molar mass for that element. 1 aluminum at 27 grams per mole for aluminum. We get 32.1 times 2 is 64.2. Oxygen is 8. Oxygens times is 16. 16 grams per mole gives us 128 grams per mole. All of these add up to 258.3 grams per mole. That being said, we have to acknowledge that there's uncertainty. There's uncertainty around those individual molar masses, and when you add up values where you've got uncertainties, you're actually accumulating more uncertainty because you're adding these values. This goes back to the uncertainty section in Unit 2. Not going to review that just now, but suffice to say, it's going to be about 258 grams per mole. Now, water. Water is a lot simpler. H2O, 2 hydrogens, 1 oxygen. Each hydrogen is 1 grams per mole. The oxygen is 16. By the way, you should memorize those molar masses. It'll make your life easier. 1 gram per mole for hydrogen, 16 for oxygen, 12 for carbon. They come up a lot. The 2 hydrogens plus the 1 oxygen give us a total of 18 grams per mole. I think I'm probably not going to burn my fingers now if I do this mass, so let's make it happen. Still pretty hot. I don't care about my fingers, but I don't want to do anything to my scale. There we are, 21.40 grams. And that's all we need. The mass of the dried sample plus crucible is 21.40 grams. Now, that's the mass of the dried sample plus crucible. We're going to subtract the mass 20.63. So let's do that. 21.4 minus 20.63. Okay, and I get the calculated mass of the anhydrous compound is 0.77 grams. How much water is in there? The hydrate was 1.40 grams. The dried sample was 0.77. So 1.4 minus 0.77 is 0.63. We have 0.63 grams of water that were lost when we dried out that crystal. How about our chemical amounts? Remember, and this is one you should also, I talk about not having to memorize formulas. This is one I would memorize because it'll make your life easier. If you want chemical amount, and I give you mass, you take your mass, divide it by the molar mass, and that'll give you your chemical amount measured in moles. Mass divided by molar mass is chemical amount. It comes up a lot, so you should remember that formula. Now let's take our mass values. Our anhydrate had a mass of 0.77 grams. And water, 0.63 grams of it were lost. Let's see how this turns out. 0.77 divide by 258.3. I only get 2 significant digits. 0.0030 moles. Always pay attention to what are the units that you're working with. Here it's moles. Water, 0.63 divided by 18. 0.035 moles. The ratio will be, what do you get when you divide one by the other? Well, let's see. We're dividing the potassium aluminum sulfate by the water. So I'm going to go 0.77 divided by 258.3 equals, I can divide that by bracket 0.035 divided by 18. That was the other chemical amount. Notice when I do this, I'm doing everything from the start, so I don't make any rounding errors. You don't find a value, round it, find another value, round it, and then use that to make your final calculation. Use the rounded values. That's a no-no. You want to keep your rounding to the very end. This is very important for when you're doing physics. Oh. Okay. 0, 0. All right, I'm going to try that again. 0.77 divided by 258.3. Oh no. It's got to be water over. Yeah. Let's try this again. We have 0.63 divided by 18. Okay. Dividing that by bracket 0.77 divided by 258.3, close bracket. Much better. And I got 11.7. Okay. That's an interesting result. Not really what I expected, I'll be honest with you. I expected that there was going to be a lower value of 8. But again, you never know in chemistry. There's always a possibility of being surprised. Maybe there was some contamination there. I don't really know, but that's totally fine. That is how you need to do it, though. You take your number of moles of water that you get, divide that by the number of moles of your anhydrate, and that'll give you your ratio. I got 11.7. We only have 2 significant figures allowed, in fact, so really I should be reporting the result as 12, which actually is really very interesting. It implies that the crystal that I made really did have a formula, just like on the box, of KAlSO4 with a 2 dot 12 H2O. I thought I made something with 8, but that's totally fine. According to this, it's 12. You got to go with what the data tells you, not your own pie-in-the-sky ideas. We're next going to do this with copper sulfate. For this, I'm going to rely on you to use the same kind of steps that I used when I just demonstrated the lab with this material, but we're going to do it with copper. There might be a bit of lag time in this video. I don't know how to edit these things, so you have to be patient. This is the crystal of copper right here. Why do you think, by the way, I chose a big crystal instead of a bunch of tiny crystals? That can be some food for thought for you. Why did I find the biggest crystal I possibly could to do this lab activity? That's going to come up in the question set. We're also going to look at what happens. I'd like you first of all to see the color of this crystal. There's a nice close-up for you. It's a very large crystal of copper sulfate. And we'll get our measurements. So first of all, I don't expect there's going to be any change in the mass of my crucible. I'm going to clean it because that's what you should do, and then I'm going to make sure it is dry by putting it on the Bunsen burner. If I was better at managing time, I would have a second crucible, but these don't take long to dry out. So a reminder while this dries out that what I'm going to do is I'm going to measure the mass of the crucible. I'm going to put the crystal in. Then I'm going to measure the new mass. Then I'm going to put this whole contraption, the crucible with the crystal in it, onto the Bunsen burner. It's going to take a little while to boil off. You can just fast forward through the video while it's boiling off. Do whatever you want. Once we get to the end is when I'll have the results for you. And again, the results is going to be how much did the hydrate weigh to start, how much did it weigh at the end. From that, you can calculate everything else. You can calculate how much water was lost based on the molar masses of the copper sulfate and that of water. You can go forward from there and you can calculate the formula for that hydrate. I'm not going to tell you how to do all of this. I will give you some hints. At this point, you might even want to click forward something like 6 or 8 minutes. Or just a few minutes while I wait for this to dry out. I've run out of stuff to say. All right. Hopefully you're still with me. I'm going to start the experiment with the copper sulfate. This tends to go pretty quickly. And there it is. This is the crystal. Now it's inside the crucible, and the Bunsen burner is going. I've measured these masses so far. The mass of the crucible, I don't know why, it lost 0.02 grams. No problem there. The mass of the crystal in the crucible, 23.07 grams. That's a big crystal. It's already going. It's just starting up. You can hear that hissing sound. That hissing sound is the boiling of water inside the crystal. Very soon that's going to start to break the crystal apart. I'm going to use this stirring rod to try and make the process happen a little faster. And it is not happening. That is one big crystal. But the color is changing, which is exactly what we're looking for. So I will get the I'll get the camera focused on the crystal. So we're starting to see a color change right there. Color change is something that you should also be taking note of for the purposes of this lab. Hydrate salts of transition metals are often very pretty and colorful. When you remove the water from the crystal structure, often it changes the color, which looks to be what's happening right here. Check this out. Isa, would you hold the computer for a sec? Like this. Exactly like that. I want to show the students some fireworks. See that change in green?
Whoa.
Yeah. That's totally not part of the lab, but it's kind of cool. One thing that transition metal salts often will do as well, when you expose them to, or many metal salts, when you expose them to a flame, a high heat, tiny amounts of those ions will escape into the air, and having done so, they will then they can then actually release light. They're very excited ions. Their electrons jump back down and release light of a characteristic wavelength. For copper, that wavelength is the wavelength of blue or bluish green light. And so when you flare copper salts, you tend to see a green color. Was any mass being lost from a crystal while I did that? Maybe a tiny bit. Is it likely to affect the results? I don't really think so, because it's really small amounts of the salt that are always involved in those kinds of reactions. Let's get the lights back on. We'll have a look, see what's happening. And there. So this is the product. The product is an anhydrous salt. Just like before, we saw with the aluminum, it changed the crystal, which used to be a large crystal. It broke apart into, they're still crystals, but they're now microscopic crystals. It doesn't look anywhere as pretty as it used to. But do notice the color changes happened here as we went from the hydrate salt to an anhydrous salt. Another observation I would make here is that there does appear to be a lot less, which there really is. The water is a significant part of the mass of the original crystal. I've now made it into a very pale colored, fine powder. It's very dry. I can tell that much. Good enough. I'm going to turn off the burner. I'm not going to put this right on top of the scale because I might wreck my very nice scale. So again, you might want to fast forward the video a few minutes, or maybe I'll learn how to edit these things. Do you know how to edit videos?
Mom does.
Yeah? Okay. I don't know about this file type.
Look at my chess game.
You ruined our chess game. You were playing a very good game. That's too bad.
No. That's what you like to play.
That's not a chess game anymore.
Half of the pieces are queens. This one took me a long time ago. Are you done the video?
Stop. So, this is the final product. I'm seeing, looks like the weight is actually fluctuating a bit. Let's just have one more look. I'm gonna go with that. As the final mass of a dried sample plus crucible, the figure I'm getting is 22.23 grams. So again, the crucible was 20.61 grams. Hydrate plus crucible was 23.07. The mass of a dried sample in the crucible was 22.23. From that, you should be able to calculate the mass of the anhydrous salt, the mass of the water that was lost. You know the molar mass of water. You also are going to need to find, and this is where there's a bit of a thinking cap here, you will need to find the molar mass of copper sulfate, but I mean the molar mass of anhydrous copper sulfate with no water in it. If you Google molar mass copper sulfate, it's probably going to give you the molar mass of a hydrate. You don't want that. Copper 2 sulfate is CuSO4. 1 copper, 1 sulfur, 4 oxygens, and that's it. If you use those figures to get the molar mass, then you are going to get the correct result. I don't know what the result's going to be for this lab. After you're done the lab, you're welcome to look up what the common hydrates are for copper sulfate. But as it is, I'm not going to tell you. I'm just going to say do the calculations, and see what you find. I hope that helps for this lab.